Hello everyone, welcome to part 2 of the Positron lab. We are so glad you have rejoined us. You will note before you that there is a slight reconfiguration from the previous lab setup, and most of this is simply due to lab logistics rather than any experimental change. You will notice before you, sitting on the sash of the fume hood, a GLX instrumentation device. This will collect our data from our two radiation detectors, the sodium iodide scintillator detectors that you see in apposition to one another across the reaction chamber in the fume hood. You will also notice that the same arrangement still obtains. We have a chamber here with iodine in it. It is being heated now, so you may see a slight purplish vapor. We're not ready to start our run yet. We're letting that heat up. You'll notice the airlines. There's an airline supply to your right that you see coming in, and then the middle stopper will be the outgoing beam line, and this is what actually replicates what will ultimately be in the beam line. We are not using the electrically or electronically suspended or electromagnetically suspended, depending on the nomenclature you wish to use to describe our beamline today, simply because we're wanting to check for iodine flows. In the iodine chamber, you will also notice suspended there a sodium iodide, a sodium 22 source. It's a 1 microcurie, so very low activity. However, sodium positrons complex very well to iodine. Iodine also carries very well. It's a highly visible marker. You will note the purplish gas that will be emanating. It right now looks very much like a rosy color, but we'll turn up the heat in just a little bit once we start the benchmark experiment going. This will then flow into this gas measurement device, and you'll see there a flow meter, which right now is sitting on 0. This then comes into the reaction chamber, and then you will notice the main reaction chamber across which the two sodium iodide detectors are placed. We will note also that there is a water jacket. We'll start the water in just a moment to keep this at a room temperature so that we can observe adiabatic positron transport. You will also note that we will have the iodine vapor going out through the X current tubing, which is marked by this cork stoppered region at the upper left-hand corner of the iodine tube. So let us begin our experiment today. If you'll stand by for just a moment, we will turn up our heat on the iodine so that we have a larger, bring it closer to its melting point. And then we will also be observing the temperature of that chamber, which right now is sitting at around 20 degrees Celsius, I seem to see there. So this will be confined in the fume hood. We'll bring the sash down, and we'll go ahead and turn on the blower. We will also run the detector here, which will be gathering the data from our two sodium iodide detectors. Before you, you will see simply a meter stick placed for scaling purposes. Thank you for your patience. Let's go ahead and turn on the fume hood. The blower will be quite noisy. I apologize for that, but I'll do my best to speak above it and try to keep the camera as far away from the blower as possible. And then once that occurs, we will then turn on the water. You will notice that in the fume hood that we now have vapor arising, and so I will continue to let that heat for a while. We'll start seeing some really wonderful dark purple vapor. So we will now start the airflow, just a very slight airflow into the system. So now we have the air flowing as indicated by the rolling ball that you just now saw. And we now have the air flowing into the reaction chamber here. And we will not start our scintillator detectors counting until we have the purple vapor observed over here in the reaction vessel. Now here comes the blower. It is also exerting a negative pressure. We're not dealing with any toxic materials. Again, our sodium iodide source is only a 1 microcurie source. Count rate right up against it is less than 1,000 counts per minute. That's on contact counting. And then back here, the dose rate is well below background, where we are standing and filming this. Observe as the iodine reaches its melting. You'll notice now the beam line carrying the iodine vapor away from the source chamber over to the reaction vessel is now turning a purplish color, and after a longer run this will turn a gold coloration. So now we know that we have some vapor reaching over into the reaction chamber, and by inference we know that we also have positronic activity over here, and we will confirm that positronic activity by running the GLX with the coincidence counters. Okay, notice we now have a nice strong red, purplish red vapor coming from the iodine, which is exactly what we had hoped for. And before I turn on, and we will now at this time turn on the water into the reaction chamber so as to maintain that at close to room temperature conditions. This also serves the purpose if we have outgoing iodine vapor, the water in the drain will also carry that with it. It's non-toxic. Iodine is also used in many settings for antiseptic purposes. So it is a non-toxic chemical and makes an ideal marker, as we have said. I'm going to realign the sodium iodide detector here so that they're exactly across from one another, and while we're waiting for the vapor to begin running through, let's take a quick look at our board here in the lab. Now you will notice up on our board that we have here the electron marked by the E negative in the black, as well as the beta minus radiation. Beneath it, we have the blue electron marked E plus, a positron rather. So on the top is the electron, which is matter. On the bottom is antimatter, positron, the antiparticle to the electron. It is a fundamental particle in physics. What you notice there is the diagram where they come together at that X shape. And when matter and antimatter come together, they annihilate, and all that matter is converted into energy according to E equals mc squared. It sounds as though it's the stuff of science fiction, but it is not. I assure you that we have it here in the lab. That's what you just saw going on in the fume hood. So, you will notice that each of them has an energy, a distinctive energy signature, 511,000 electron volts, or 511 keV, as we say in the field. And so the electron has 511 keV, as well as the positron has energy at 511 keV. When they annihilate, then we can add those two energies together for a whopping 1.022 million electron volts. And when we perform a gamma ray or a gamma spectroscopy, we will see a big peak at 1.022 MeV. So that's exactly what we're doing today. We will see, coincidence counting, we will see 1.022 MeV measured on our graph. And we are using coincidence counter because it will also measure those electrons and positrons that did not react and did not annihilate. And so we have some of those that did not annihilate that complex to the iodine, and that is known as positronium. In this case, it's gas positronium. So now let us return to our fume hood as it's in operation, because we now have a bright purple iodine gas, and we're now flowing that into our fume hood. And you will notice that it is coming into our reaction chamber. And you will notice that we will turn up our flow rate at this time to get some more into our reaction chamber. You will have to excuse the noise, but I want to place you, the viewer, close to the reaction vessel so that you can see. We will now cease recording this part 2, and then we will come back later for an analysis of the data. Thank you again for joining us in the Positron lab today. We hope you have fun in science, better living through science, and even better living through antimatter.